I'm Deborah, and I'm a physicist. And today we're going to talk about things that are moving in just one dimension, specifically things that have a constant acceleration. This is something. We don't really know what it is, and it doesn't really matter. It's a blob. We're not going to worry about its physical size or even how heavy it is today. It's just something. But even if all we know is that this something exists, there's a few other things we can know. We can know where it is. We call that the position. We can know how fast it's moving. We call that the velocity or the speed, the technicality we'll talk about later. And we can know if it's speeding up or slowing down. We call that the acceleration. The study of all of these things is called kinematics. Now, what does it mean for something to be moving in one dimension? Well, that means it can go from left to right. It can go from right to left. We call that moving in the x direction. Or it can go up. We call that moving in the y direction. Or down, also moving in the y direction. But it can't do both at once. It can only move either left and right or up and down. Now, we're going to talk today about moving with constant acceleration. And there's some equations we know that are just sort of standard that work for any problem where you have a constant acceleration in one dimension. If you're moving left and right, you'd say that the acceleration a sub x, the x part of the acceleration, is equal to a constant a. Then the velocity in the x direction is an initial velocity, however fast you were going when the acceleration started, as well as that acceleration times how long you've been accelerating. And then your position as a function of time is any initial position where you started from, that initial velocity, how fast you were going when you started accelerating, times how long you've been accelerating, plus your acceleration divided by 2 times the amount of time you've been accelerating squared. Now, this is exactly the same when we're moving left and right in the x direction, or when we're moving up and down in the y direction. Same exact equations, we just swap all the x's for y's. Now, these are pretty random seeming equations. If you're taking an algebra-based class, it's likely that your professor or your teacher just gave you these equations and said, this is the equations for constant acceleration, one-dimensional motion. And you might be saying to yourself, why? How do I know this? Did someone just move balls a lot to try to get this information for me? Is there some reason why this would happen? There is. It's called the magic of calculus. And the someone that helped us get there is Isaac Newton, or Leibniz if you're a Leibnizian person. But the magic of calculus lets us actually take a simple piece of information and create these equations for ourselves. So if you're in a calculus-based physics class, this is probably a review. If you don't know calculus, this is still going to kind of look like magic, but I promise it is math. Okay, so if I have position and I want to get to velocity, I take a derivative. And if I have velocity and I want to get to acceleration, I take a derivative again. These are all time derivatives. One way you can tell that this is what's going on is that you're adding an extra factor of time in the denominator of your units. What do I mean by that? Well, the unit of position is something like a meter, and the unit of velocity is something like a meter per second. How much time did it take you to go that distance? And your unit of acceleration is something like a meter per second squared. So every time you take a derivative, you add an additional factor in the denominator of seconds. So position to velocity, that's a derivative. Velocity to acceleration, that's another derivative. As an aside, the derivative of acceleration is called the jerk, but you're most likely not going to need to know that. Now, anything you can do a derivative, you can also do an integral, which is just undoing a derivative. So we can take, to get velocity from acceleration, we take one integral, and then to get from velocity to position, we take another integral. As an aside, if you've heard the term double integrals or triple integrals, that's not what this is. This is just doing multiple integrals in sequence. Double and triple integrals are doing integrals with more than one variable. These are all with respect to time. Okay, so let's actually do that. If I tell you that you have an initial acceleration a in the x direction, and I want to know the velocity in the x direction, I would do one integral. So I would say b of x as a function of time is equal to the integral of this acceleration, the function overall, with respect to time, which is the same thing as the integral of this constant value a, or a times t plus a constant. So we'll call it v0. So we remember that that constant has to have the units of velocity. It has to be some kind of velocity. So if you look at the starting point and the ending point here, we've ended up right back at our expected vx of t is the acceleration value times the amount of time we've been accelerating plus whatever velocity we started at. Cool. Now if I want to get position, I just do that same thing again. So now I say x as a function of t is the integral of v of x as a function of t with respect to t, which is the integral of at plus v naught. All of that is dt, which is in turn, down here, a over 2 t squared plus v naught times t, plus again some constant, which we'll call x0, so we remember that it's a constant that has the units of position. And here again we have x of t, just like we did before. What if we know the position and we want to get the acceleration or the velocity? Well, we're just going to do the exact same thing in reverse. We're going to take derivatives instead of doing integrals. So we start up here at x of t is this value, and we want to know vx of t. Vx of t here is the derivative with respect to time of x of t. We could also write this, by the way, as x dot of t. That's another way of writing time derivatives. At any rate, that derivative, we drop the constant, we drop the one factor of t off of v naught, and then we bring down that exponent, a over 2 times 2, gives us a times t. So we're back where we expected with v of x. And likewise, if we want to get the acceleration out, we do one more derivative. So we go ax of t, and we would say this is d dt of vx of t. Or we could say that this is d dt of x. Or we could say that this is x double dot of t. All just different ways of writing derivative. At any rate, we're going to again have ax of t is drop the constant entirely and remove one factor of t there. So we get ax of t is a, which is right what we started with and exactly what we expect. If you're not a calculus user, the last two slides probably kind of seem like witchcraft. That's okay. This is just one other piece of math that can help us understand how we got these equations. One of the beautiful things about physics is that pretty much nothing just came from the sky. There's a reason why we have the information we have for every concept. Okay, this is not rocket science. Generally speaking, one-dimensional kinematics is pretty straightforward. Either you have your equations, or you can get them back really, really easily with just a couple of derivatives and integrals, and for constant acceleration, those are pretty easy derivatives and integrals. So it's not rocket science, except when it is. Let's do an example. Suppose we have a rocket that's launched directly upwards with a constant acceleration of 205 meters per second squared. How long will it take the rocket to travel 1,500 kilometers? Well, let's break this problem down. The first thing I notice before I do anything else is that actually these units don't match. I have meters and I have kilometers. So the very first thing I'm going to do is write down that I have an acceleration of 205 meters per second squared. And my final distance, my y final, y sub f, is 1,500 kilometers, which I know, because I can know my SI prefixes, is 1,500 times 1,000 meters. So therefore, I switch to scientific notation, and I'm going to write 1.5 times 10 to the 6 meters. I want my acceleration and I want my position to have the same units so I don't get confused later on. Beside my given information, the acceleration, and also my final position, and I've also converted those to all be in the same units. What will I do now? Well, one thing I can do is draw a little picture. Do we need a picture for this? No, not really. We kind of understand how a rocket will launch upwards. But it can be helpful for us to think about things graphically as well. By drawing a picture is to set what direction will be positive and what direction will be negative. We tend to think of up as being positive and down as being negative, but we don't actually have to follow that rule, and there may be problems where it makes more sense to define things the other way around. One of the great things about physics is we can just define things however we want, so long as we make it clear what we've done. So I'm going to write a little coordinate system here that just says, hey, up will be the plus y direction. And I can imagine a little picture here. This is my rocket. This is a rocket. And it's going upwards. There's not really much I can draw here. I just have one-dimensional motion. So we imagine a rocket. It's launching. Okay. Now we might ask ourselves, now that we have our given information and we have our coordinates, what am I trying to find? What will the final value of my answer be? What kind of units will it have? Well, the question asks us, how long will it take? And that means my final answer will actually be a time. So I need to know an amount of time it takes to go a certain distance. Y final. So what am I going to need to find that? Well, I'm going to need an equation for the position of my rocket as a function of time. And I know going in what the acceleration is, that it's a constant acceleration, it's not changing, and it's 205 meters per second squared. Now I could go back 2 slides and look up my equations, but I'm a bit lazy for that, so instead I'm going to redo my integrals and get from my acceleration as a function of time to my position as a function of time. So I will get that the velocity of the rocket after a certain amount of time is the integral of the acceleration, dt, so it's the integral of a0 dt, which gives me a0 times the amount of time plus whatever the initial velocity was. Now this is a bit of a mistake I made in writing this problem. I should have told you what the initial velocity of the rocket was. However, given that rockets generally start from rest, we can make a reasonable assumption that v0 is 0 meters per second. The rocket is not moving when we start, and so we say that we have the velocity is just the acceleration times t. Now, why am I using a0 when I know the value of a? I know that a0 is equal to 205 meters per second squared. So why not just write 205 meters per second squared? This is actually a great physics hack. It is much, much easier to follow your work if you leave things in symbolic values that tell you this is an acceleration, rather than switching to specific numerical values that can be hard to track. So it's a lot easier for me to keep track of my work when I'm using symbolic representation. As a bonus, if you're in a classroom environment or you're talking to a TA or a professor or a teacher, it's much easier for them to find mistakes in your work when you give them information like this was the acceleration at a glance. Okay, now I really want to know about time it takes for me to travel to a specific position. So I actually want to get y of t. So I'll take another integral of dy of t with respect to time, and then it'll give me I'll be integrating a0 t dt, which is a0 over 2 t squared plus, well, I know I don't have any initial velocity, so that's 0 t, plus, I'm guessing I start at 0 meters, assume that the rocket is on the ground at the 0 point. So then I can just say that y f equals a0 divided by 2 times t squared. We want to find the time where this is true, and so we can move everything away from t. So we say that 2 divided by a0 times yf equals t squared. And finally, we'll take the square root, and we'll get that t is equal to the square root of 2yf divided by a0. And now the time has come to put in numbers. Time is equal to the square root of 2 times 1.5 times 10 to the 6 divided by 205. And that gives us a value of 120.97. 120.97, and we always want to include a unit, so this is in seconds. Now, how many decimal places you should include in an answer is actually kind of a complicated question. There are 3 significant figures in our given information, this 205, and so we might round this off to 121. On the other hand, your class might also have a different policy, and you should always follow what your teacher tells you to do in terms of significant digits or decimal places. Now, a car is traveling at 6 meters per second in the x direction, and it starts accelerating at a constant value of 4 meters per second squared. How fast will it be going after 7 seconds? Okay, so in this problem, we have all of our given information in the same matching units, which is great. So let's go ahead and just summarize what we know. We know that the initial velocity, v0, is 6 meters per second. We started off going 6 meters per second. We also know that the acceleration that kicks in as that time equals 0 will be 4 meters per second squared. And our final time, the time we're worried about, will be 7 seconds. We also know that we're just moving in the plus x direction. So this is plus x. And so now we're ready to solve for how fast the car will be going after 7 seconds. Now, what is that final desired outcome? Well, that's a velocity. So velocity at TF. Okay, so we have the acceleration, A of t, equal to, again, we'll call it A naught. And we can again take the integral and do Vx of t equals the integral of A naught dt, which is equal to A naught times t plus our initial velocity. Now we do have an initial velocity this time, and so we'll want to include that. And now this is actually quite straightforward. We just need to plug in our time. So Vx of 7 seconds is equal to A naught times our t final plus our V initial, which is the same thing as 4 times 7 plus 6. And this is 28 plus 6, which is 34 meters per second. Done. On the planet Zargon, there is no air resistance, and the gravity is unlike our own planets. A feather is dropped on Zargon, and it falls 16 meters in 2 seconds. What is the acceleration due to gravity on Zargon? Now this is kind of serving two purposes. One is that I wanted to do a problem where we turn it around and find an acceleration, and the other is this is actually an example of a kind of problem we call free fall. So in free fall, you have some object and you drop it. It accelerates with an acceleration based on the gravity of the planet you're on, and you can calculate all kinds of things. Usually in free fall problems, we'll also exclude air resistance. But if you're unsure on whether you should include air resistance or not, as always, ask the person who gave you the problem. Okay, so we have a feather, and we're dropping it on this other planet, and we know that the final position, y final, is 16 meters. And the time final is 2 seconds. We want to know the acceleration. Now this is a great example as well of how we can define signs exactly how we want. So before, we usually defined 0 as at the bottom and plus y going upward. But for this problem, I'm actually going to define plus y going downwards because I know that my feather is falling, and I don't really want to work with negative numbers if I don't have to. I can just say, hey, the feather is falling, positive is down. So I do that, and now I know I want to know an acceleration. Now I know that whatever this acceleration due to gravity is, it's some kind of constant. We can assume that the planet Zargon has a constant acceleration due to gravity. Okay, so we say that the acceleration in the y direction as a function of time is equal to some value A naught. Here's the trick. That's actually what I'm solving for, is this A naught value. So again, we'll have to get back to an equation for position. So yet again, we'll take an integral, integrate A0 dt, and that gives us A0 times time, plus maybe an initial velocity. But generally speaking, when we drop something, we don't throw it down with its intense initial velocity, so we take v naught to be 0. This is a little physics trick. It's quite likely you'll receive problems that say something is dropped and intend for you to assume the initial velocity is 0. Okay, so then our position, y of t, is, again, we can integrate. And again, if you're not comfortable with integrating, that's totally fine. You just pull out those standard equations we had a couple slides ago and use those. So again, we get a naught over 2 t squared. Okay, and now we're going to solve for a naught. So what we're going to do is we're going to move this 2 to the other side, and we're going to move this t squared to the other side. So we have 2 times y final is equal to a naught times t final squared. And then I can move that t final over, and I know that a naught is 2 y final over t final squared. I plug in my numbers, 2 times the final distance, which is 16, divided by my final time squared, which is 2. I can actually cancel that squared and that 2, and my final answer is that the acceleration due to gravity on Zargon is 8 meters per second squared. All done. So what does it mean that the acceleration due to gravity on Zargon is 8 meters per second squared? Well, the acceleration due to gravity on Earth is 9.81 meters per second squared, and that means that the things fall slightly slower on Zargon. This suggests that you would weigh a little bit less on Zargon as well. So it's a weight loss plan to move to an alien planet. So what have we learned today? Today we've talked about one-dimensional kinematics, motion moving just left and right or just up and down. We came up with the equations that govern this, what we can use to solve for positions, velocities, and accelerations. And we also tried a couple of examples. This is Not So Scary Physics. I'm Deborah, and I hope this whole thing wasn't so scary.